Today we're going to be looking at a video by Real Engineering. This one is called The Economics of Nuclear Energy. For those of you who don't know me, I'm Tyler Folse. I'm a nuclear engineer with a little over 10 years of experience in the commercial nuclear power industry, from engineering to operations to emergency response. I don't claim to know everything there is nuclear, but I can certainly share some knowledge. Check it out.
In our quest for clean and cheap energy, massive solar and wind farms have sprung up across the world. Investment in these renewable resources reached $273 billion in 2018. Include the 8 previous years, and that figure reaches $2.3 trillion. This is positive news for most, but many have been left asking, why not nuclear? After a quick examination of countries' carbon dioxide output per kilowatt hour of energy produced, it becomes clear that countries like France are currently doing better than countries like Germany in that quest to produce low-carbon energy.
That's right. Nuclear is extremely high volumes of energy and carbon-free.
France, with 61% of its electricity generation from nuclear, is producing just 32 grams of carbon dioxide for every kilowatt hour produced. Where Germany, a country that has invested billions into wind and is gradually closing down all its nuclear power plants and replacing them with natural gas plants and wind energy, is producing 318 grams of carbon dioxide for every kilowatt hour.
That's so
perfectly understandable why.
And this video, I will add, this video is a few years old. That's why it's still showing Germany having nuclear, even though they don't anymore, which is very, very sad.
Advocate for nuclear energy over renewables. Wind itself releases less carbon dioxide for every kilowatt hour of energy it produces at about 11 grams, just under nuclear's 12 grams per kilowatt hour. But because wind is intermittent, it needs to be propped up by some form of power production that can quickly ramp up and produce electricity when the wind falls, and natural gas is the perfect solution for that at a reasonable price.
Yeah, you don't want an entire grid to be run on wind and solar. Lack of storage, intermittent, it's just a mess. The advantages of wind and solar is an individual unit is small and relatively inexpensive, so they're modular, so you can have them provide power to small areas, and you can also quickly, if you just need a little bit more power, you can build a few more megawatts of wind turbines, for instance. But they don't last very long compared to nuclear. Best case scenario, we're talking 20 years from like the best wind turbines, but those wind turbines are actually pretty expensive relative to the typical ones that last on the order of 10 years. So I can see why the rise, and you mentioned earlier about all the additional investment. There's been plenty of small solar and wind startups just because I can see how they have that potential attractiveness for investors, albeit you have the risks associated with investing in a startup, but it's a lot easier to pull those resources together.
So in reality, wind isn't competing against nuclear energy, at least not directly. It's competing with larger baseload power stations like natural gas, and to see why it's losing that battle, we need to dive into the world of economics to see why countries and investors are shunning nuclear energy. When choosing where to invest money in infrastructure, there are several factors you need to consider. Risk, potential gain, and the time it will take to get a return on investment are the most important. This is an extremely simplified example of a return on investment calculation for 2 power plants, a 1,000 megawatt nuclear power plant and a 1,000 megawatt natural gas power plant.
One thing to point out is 1,000 megawatts is pretty common for nuclear, but it's less common for natural gas. It's not to say you couldn't make one, but typically nuclear power plants are larger. Not to say there aren't 1,000 megawatt natural gas plants, because there have been more recently compared to historically. But another thing is you can also have nuclear power plants that are larger. The one that I worked at had 2 reactors, and each one of them produced 1,400 megawatts. So there is a little bit of variation in size. A typical natural gas plant is 600 to 700 megawatts.
This calculation is based on the wonderful video on the Illinois Energy Professor YouTube channel, which I will link in the description below. When making this kind of calculation, we have a few variables we need to consider. The cost of construction, the fuel cost, and the construction time are the biggest variables that differ between the two energy sources. The average cost of construction for a nuclear power plant is a difficult number to pin down.
Those are the biggest, but one that I would probably add right below that is the cost of downtime. Nuclear power plants can run for 18 to 24 months. A metric called the capacity factor is used to describe how often the unit is producing power. It's 92%, some even higher for nuclear, but we're talking upper 40s to low 50s% for a natural gas plant, so keep that in mind.
The number varies widely from project to project, ranging from 5,500 per kilowatt to 8,100 per kilowatt. We will assume a lower price of 6,000 per kilowatt, resulting in a price tag of $6 billion for a 1,000 megawatt nuclear power plant.
That's actually optimistic in light of, but $6 billion sure for your base cost, but construction takes so long it's subject to cost overruns. We look at what happened with Vogtle 3 and 4, which when this video came out are still both under construction. Vogtle 3 is online now, which is good.
Natural gas, on the other hand, is one of the cheapest types of power plants to construct, with a cost of about $920 per kilowatt. So, a 1,000 megawatt power plant would cost $0.92 billion. But let's just round that up to $1 billion for simplicity's sake. Now, I know you already see the problem. Natural gas is just cheaper, and it's going to take the nuclear power plant longer to recoup that cost. This becomes even more of a hare and tortoise race as a result of the construction time of each. The average nuclear power plant takes 6 years to construct, whereas your typical...
That's fast. I'd actually like to see 6 years for nuclear. If you look at how long Vogtle 3 and 4 did, though the plants in the UAE were shorter. The challenges is it's been so long, and it's going to get faster. I believe it can hit 6, but in the US, it's been so long since we built a nuclear power plant, a lot of it we kind of forgot how. So this estimate right here might actually be favoring nuclear a little bit.
Natural gas power plant takes about 2 years to construct. This becomes a particular...
That's fast, though. That's fast too, though. But I still think nuclear is going a little bit faster relative to natural gas than it can. Because natural gas, they can take 4, but nuclear can take 15, so for the comparison, as long as we get the ratio sort of right, I still think his ratio is favoring nuclear a little bit.
Issue when borrowing and interest rates are involved. We are going to assume an interest rate of 3% and a repayment term of 25 years for both plants, and both will borrow in $1 billion increments. $1 billion on a 25-year repayment plan at a 3% interest rate equates to a $56.7 million payment every year. Here, we will borrow an idea from the Illinois energy professor to illustrate profit and loss with blocks. Below the x-axis, these blocks represent debt. Above the line, they represent profit.
Okay.
We will place nuclear's profit and loss on the left side of the graph and natural gases on the right. Each full block unit, like this, represents $56.7 million.
This is a very simplistic explanation that I really like where he's going with this. Just a good apples to apples comparison. Granted, there's several underlying assumptions here, but I like the simplicity.
These blocks can be partially filled to represent smaller fractions. We are using this to bring the vast quantities of money involved into a more human scale. Let's begin. In the first year of construction, both plants will generate 1 unit of loss, as both borrowed $1 billion. In the second year, the nuclear power plant borrows another $1 billion, so it now owes the bank double the repayment. So it now has a total of 3 units of loss. Natural gas does not borrow another $1 billion, so it just needs to pay off the current 1 unit of debt owed yearly for a total of 2. The natural gas plant is now complete. It took 2 years. It can now begin to generate revenue to turn that loss into a profit. Now we need to calculate revenue. Both are 1,000 megawatt facilities, meaning if they both run for an hour, they will both generate 1,000 megawatt hours of energy. Calculating revenue from this number is not straightforward. As the energy marketplace is complex, grid operators may buy a large
It's especially complex in places like Texas, where with the deregulated market and ERCOT's kind of its own separate entity from the rest of the country. So although if we're talking base load, a lot of those ramp up numbers are at the margin. So if they're both base load, you can at least compare it apples to apples, even though, as in, you can make a similar assumption about both. Though I will say, one of the key differences is nuclear does have right-of-way over natural gas because it's typically in much larger quantities, and they do take longer to start up from a fully shut down condition. Now, they're on a lot longer, but it's much better for grid stability to turn the nuclear plants on first.
Of nuclear's base load out in advance for a set price, as it can't turn itself off easily. It needs to continue.
It can turn itself off very easily. It can't turn itself back on very easily. I know that's what he meant, but just a clarification. You can shut down a nuclear plant in less than 2 seconds. Just press the reactor trip button.
Run, and electricity prices drop in the middle of the night as demand falls. Energy prices constantly fluctuate, so it makes sense for nuclear power plants and the grid operators to agree on a bulk price. Whereas the natural gas plants can operate as peaking plants, shutting down during the night and only operating during the evening when electricity demand and prices are at their peak.
They can operate as peaking plants or load follow plants is another way of referring to those, more readily than nuclear, but compared to wind turbines or solar, they don't have quite that level of flexibility. Granted, that's just because it's a large thermal cycle system. It still takes time to start up and shut down the secondary part of the plant. That is identical to nuclear, but it's not going to take you nearly as long to start the boiler being their substitute for the reactor,
allowing them to fetch a better price for their electricity, thereby losing less money on operation and maintenance of their plant and getting the maximum profit out of their fuel spend.
I don't see how that reduces their costs. Maybe he's just talking. I think he may have done a step ahead of just how of their revenue minus their costs, because the costs aren't really going to change, and the costs of the secondary, the turbine and generator part of the plants are going to be roughly identical, just because it's a very similar system. The nuclear plant that I worked at actually had a similar turbine to a natural gas plant that was a couple hundred miles away.
In transmission costs, as energy is lost to power lines, taxes, and all the other messy factors, and it becomes even more difficult to calculate earning figures. This calculation will be inaccurate. We will make a massive assumption and assume they will both earn the same amount at $525 million a year after all these deductions are made. So,
wow, okay.
In its third
At least he
year,
admits it's
the natural
inaccurate.
gas plant will have a revenue of 9.25 of these blocks. After our loan repayment, that will be 8.25 blocks of profit. But there is another large deduction we need to consider that differs greatly between these power plants: fuel costs. Here, nuclear has one big leg up. Its fuel is relatively cheap,
Yes.
just by virtue of only needing.
One thing, I don't know if he's going to get to it later, but did he mention the capacity factor at all? Because he said they produce the same amount, which is just not true. Nuclear produces almost twice as much, just based on capacity factor. You need to take that number that he calculated, multiply it by 92% for nuclear and about 50 for natural gas.
a very small amount in comparison to natural gas. A single uranium fuel pellet with the diameter of an AA battery has the potential to release the same amount of energy as 1 ton of coal or half a ton of natural gas. A little goes a long way. To run the 1,000 megawatt facility for an entire year, you would need about $64 million worth of fuel, or 1.1 currency blocks.
One interesting thing is on budget lists you see at a nuclear plant, because the reactor and fuel engineering supervisor actually has a very high budget, bigger than some executives, because he's the guy that actually buys the fuel. So low first level manager position can actually have his team can actually have a larger budget than a mid-level executive's budget. Because let's say that executive has a budget of $10 million. Well, this guy has a budget of $80 million for the fuel, or something like that. It's kind of funny to see that on expense reporting.
To produce the same amount of electricity, the natural gas facility would need about $450 million worth of fuel, or 7.9 currency blocks. These prices will also fluctuate, but again, this calculation is simply for illustrative purposes.
Gas is pretty inexpensive compared to even coal, but the fuel cost of nuclear is so good. And this is just existing uranium-235. Throw in some more exotic fuels once those reactors are designed. So if we design some even better stuff, there's even more potential, like thorium or breeder reactors where the reactor produces more fuel than it consumes. There's a lot of potential there's a whole lot of potential there.
So, once up and running, the nuclear power plant can produce more electricity for less money. Factoring that in, the natural gas plant will make $525 million of revenue, deduct both loan payments and fuel costs, and we are left with about 1/3 of our currency units of profit. On to year 3. The nuclear power plant borrows another billion, and so now owes 3 units of loan payments for a total of 6 in loss. The natural gas plant, however, makes 1/3 of a unit, which is removed from our loss. Year 4. The nuclear power plant borrows another billion and adds 4 units of loss. The natural gas plant removes another 1/3 of a block. Year 5. Nuclear borrows another billion and adds 5 units
upfront
of
costs
loss.
for multiple
years. The natural
years.
gas plant removes another 1/3 of a block.
So one of the reasons why they did Vogtle 3 is there was a subsidy, a guaranteed rate of return. So to help give nuclear that advantage, because you can see as an investor, you're looking at this 5 years in and we're still this much in a hole. That is one of the disadvantages of nuclear for sure. You just have to think long term, which is hard for people to do.
Year 6, nuclear borrows its final billion and adds 6 units of loss. The natural gas plant removes another 1/3 of a unit. Finally, the nuclear power plant is finished and will begin generating revenue in year 7. Deducting the loan payments and fuel cost leaves us with 2.2 units of profit. Even with the huge loan repayments, which will be paid off completely in 24 years, the nuclear power plant is making far more profit per year, but it has a long way to go in reversing this loss. Year 7, Year 8, the natural gas plant has now broken even. Year 9, Year 10, Year 11, Year 12, Year 13, Year 14, Year 15, Year 16. The nuclear power plant has now broken even and even made a profit. Year 17, Year 18,
And nuclear
Year
overtakes.
19, Year 20. Okay, you get the picture. Over the long term, the nuclear power plant is insanely profitable.
And another thing is, nuclear power plants can last for 60 years or more. The base license is 40 years, and they can get a license extension to 60, some even to 80. Now, it's going to require some capital investment to maintain the facility, but it's going to be far less than the cost of building a new one. Compare that to natural gas, 22 years. So what's interesting is nuclear beginning to get much more profitable. Well, now you're going to have to build another natural gas plant too. So that's one other thing to take into consideration. And also the capacity factor, which is going to multiply this even more. So nuclear, that's going to double nuclear's profits again relative to natural gas on this calculation. Unfortunately, this is based on the generous assumption that it would only take 6 years to build a nuclear power plant. And we're not there yet. Vogtle Unit 3 began construction in 2013 and is now in commercial power operations this year, 2023. So that's 10 years of that is gonna add up more. So Vogtle 3 illustrates the real disadvantage of nuclear, prone to time and cost overruns. And the total cost of Vogtle 3 and 4 combined is now at about $30 billion for the construction. So this makes it riskier for investors, a lot riskier. So those additional risks and all of that illiquidity, that money tied up before any profit, it's going to make the investors demand higher returns. So this 3% loan rate, you're also going to need to factor in the effective discount rate for the investors. So they're going to want a bigger percentage, the investors in the nuclear plant relative to the investors in the coal plant. And because of that, the net present value can actually be lower for nuclear versus natural gas. And net present value is one of the big decisions for whether or not to undertake any large capital project. So for investors, you're going to have an extremely good best case scenario, but there are downsides. And unfortunately, there's all these political things as well that so much can happen over the course of 20 plus years. Most investors don't think that long term. It'd be great if we did. And these times can be shortened. These profits can be raised even higher. I believe we can get there. We most definitely can. But this is the biggest hurdle.
The risk involved in reaching that profit is huge. Politicians and investors alike are hesitant to put their money on the line when 6 years in, there is $1.2 billion of loan repayments made, with no revenue on the books. With the first 6 years of loan repayments alone, you could have built another natural gas plant.
One of the reasons why the playing field needs to be leveled, because there's a lot of subsidies for natural gas too, and for renewables, but you don't see it as much for nuclear, other than that one case I just mentioned, at least within the United States. That's actually why France has so many, because they're heavily centralized and subsidized.
That's insane. Did the company take out another loan to pay for the loan payments? Financing these things is difficult. Getting that money from politicians is hard too, because most politicians aren't going to think about long-term energy strategy.
Yeah.
Because something that won't start producing electricity for 6 years and won't turn a profit for 16 is not in their interest. They will need to be voted back into office before then. Factor in that nuclear power plants have a terrible track record for running not only over budget, but over time, resulting in an even larger run into negative before revenue begins, and nuclear energy just becomes a really difficult investment to justify. That's why they are falling out of favor before even discussing the safety issues.
So here's one thing that little diagram did show. It does underscore the importance of running them throughout their entire lifespan and giving them license extensions to keep going to 60 years, because they're insanely profitable if you do that. So do not shut these down early.
Looking at these numbers, you would never expect a nuclear power plant operator to decide to shut an operational plant down. Yet, that's exactly what's happening in many places. Take the Diablo Canyon Power Plant in California. This power plant is run by Pacific Gas and Electric, a company with a diverse portfolio of energy generation: hydroelectric, nuclear, natural gas, and renewables. They are an investor-owned and publicly traded company. Maximizing profit is their prerogative. Yet, they have decided to close down the Diablo Canyon nuclear power plant.
This is me being from the future relative to this video. They have reversed that decision, and Diablo Canyon will stay open at least through 2030. Let's keep watching. Let's see if he talks about what their initial reasons were.
2024, when its 40-year license expires. Why would they do that? Well, that's complicated. First, in order to renew their license, they needed to modernize the entire facility at a cost they deemed too high. They needed to change their cooling system from a once-through system where seawater is pumped through the facility for cooling and dumped back into the sea to a closed-cycle evaporative cooling system which used the same volume of water continually and thus reduced environmental impact.
So environmental impact, additional safety investments, and sometimes you need to make upgrades based on the license extension. So they mentioned about the license fixing to expire, that's the license with the Nuclear Regulatory Commission. Certain projects need to be undertaken in order to meet that requirement. These projects can be costly, but compared to building a new nuclear plant, not very much, though it's still enough that you're going to need to find investors for it.
One particularly large cost was the cost of integrating appropriate earthquake protection after lessons learned from the Fukushima disaster, where tsunami floodwater destroyed emergency generators and caused 3 separate meltdowns and 3 hydrogen explosions. As much as nuclear
That was part of the big flex response to Fukushima. Now, what's interesting is the Nuclear Regulatory Commission didn't actually say prepare for earthquakes necessarily, because the plant that I worked at in Texas, earthquake, not really a concern. So there was no postulated event. It's more of prepare for the scenario where you lose all of your on-site electrical power sources and put in additional backup sources in safer locations, as well as give it the option to bring in more backup systems from off-site in the event that the site and the area around the actual reactor is destroyed. Because the reactor is not going to get destroyed. It would take a lot more because it's in such a hardened containment building, but a lot of the auxiliary systems are not. So it's more of, it was kind of a vague directive from the federal government. But so in Texas, we added additional defenses for hurricanes and flooding because that was the biggest hazard in our area. But California, earthquakes, sure, that makes sense.
Advocates want to say nuclear is safe, which it can be. Making it safe is expensive.
Not necessarily. Making it safe is expensive, and it is safe relative to natural gas. In terms of deaths per generation, nuclear is between 90 and 100 times safer than natural gas, and even more safer than coal.
PG&E themselves said the retrofit was too expensive and instead decided to shut the entire plant down. They decided it would make more economic sense to close this facility, replace it with renewables. This says a lot about nuclear energy.
Now, they've since reversed that decision, citing that the economic factors weren't as extreme as they initially thought. Plus, they got additional local and political support for nuclear that they didn't really count on. So that's a victory. But I do appreciate Real Engineering's illustration of their initial thought process, because these thought processes absolutely are happening when considering shutting down nuclear, and it's very sad.
When even an existing plant can't compete. It's not just nuclear energy that is facing competition. 3 hours north of Diablo Canyon, natural gas turbines were retired and replaced by battery storage. That's because California is producing so much excess solar energy that buying it and storing it in batteries to sell later makes economic sense. The energy marketplace is a complex machine, and no one-size-fits-all approach can be used. We can get a clearer picture of these costs with an analysis method called Levelized Cost of Electricity, or LCOE. The levelized cost of electricity attempts to give a simple, comparable number that represents the cost a power plant will need to charge for a unit of energy in order to recoup its cost over the course of its lifetime. The equation looks like this, but putting it simply, it's the sum of costs over the lifetime of the plant divided by the total quantity of electricity that plant will generate and sell in its lifetime. Here, we can see that onshore wind, voltaic solar power, and combined cycle natural gas are by far the cheapest forms of electricity, and this is the real reason they are gaining larger market shares. For nuclear to rise to prominence once again, it needs to evolve. It needs to compete with the role natural gas is filling. It needs to be smaller, cheaper, and safer.
Now, levelized cost of energy, it is good for having a quick snapshot, but it does have some flaws associated with it. So if you were to compare nuclear to wind and solar using levelized cost of energy and natural gas, well, it doesn't take into consideration the high capacity factor. It doesn't take into consideration how much it makes of the grid. You're not going to do a black start with wind and solar. That's just not a thing. If the grid goes down, it doesn't take into consideration the time of day, because you could be producing a lot of cheap electricity in the case of wind at the nighttime when there just isn't any demand to follow it. So in that case, while your costs are lower, your ultimate contribution to making a profit is lower because you end up with a surplus. You could have the potential to even end up with a surplus, which producing electricity that nobody wants. It also has some financial limitations, such as oversimplifying project risks and interest rates, and several other little elements and nuances associated with the cost of capital calculation. So I would take levelized cost of energy with a massive grain of salt.
Ideally, the reactor should be dispatchable, meaning it can turn itself on and off so it can fit neatly into modern grids with high percentages of renewables. A difficult problem to solve, but people are working on potential solutions that could make nuclear energy competitive once again.
You could potentially operate a nuclear power plant under load follow. It's just clunkier. The nuclear power plant I worked at was originally designed for load follow, but demand for energy went up so much in Texas that just use it as a base load, because Texas is a very energy intensive economy. So that was an interesting little study you did with the nuclear versus natural gas. I thought that was pretty good, albeit simple, but simple can be good just to illustrate a point like that. But do I think we should invest in nuclear? Absolutely. I'll acknowledge I'm highly biased, but there's real opportunity there, and we can make it even better. So even at all these numbers were with existing technology as it is now. Advances in breeder reactor technology using thorium will even further lower that fuel cost, and everything we can do to maintain our current existing nuclear power plants. I think that should be thrown in the picture, because that's something that doesn't really show up far enough, because it may seem that it's a big that argument is like an anti-nuclear, it's too expensive. I think it's just preserve what we have, and we just need to get better at building large nuclear power plants. And small modular reactors can turn that even faster. That timeline. That is the biggest hurdle, is just the really long timeline, because that's what's going to affect your net present value the most. Thank you very much for watching. I'll see you next time.